Hello everyone, I'm Ganxian Yang from Shanghai Jiao Tong University, and today I'm going to present my work titled A Formal Approach for Multi-Layered Privileges for the Enclaves. This is a joint work with Chen-Yang Liu, Zhen Huang, Professor Guoxin Chen, Hongfei Fu, Yuanyuan Zhang, and Haojin Zhu. So Professor Fengwei Zhang has introduced the basic knowledge about the trusted execution environments. So for the basic knowledge, I could introduce again. So as we all know that the enclaves or the trusted execution environments for the process, they protect the critical data from the untrusted software, or, including the operating systems and the hypervisors by both spatial isolation and the execution isolation, which means that they could using the secure CPUs and trusted on-chip modules to separate the critical data from the normal applications, normal processes, and the privileged softwares. And now many manufacturers have provided various products, including the Intel SGX, AMD SEV, ARM Trust Zone, CCA, and RISC-V systems to provide multiple products about the TE implementation prototypes. So, and the TEs are now also widely used in the various remote computation scenarios in the cloud, including the secure machine learning and the privacy-preserving services and etc. And now, there's the motivation about our work is the restriction of the current enclaves, which is lying in the usability. So as we can observe when you use the enclaves-based trusted execution environments, there are lack of the common features, including the inter-enclave memory sharing and above mentioned the memory introspection for the debuggings. And they also incompatible with some cloud or VM scenarios. For example, when we boot one enclaves, they will face the code boot problem, which means that it will cost much more longer time than a normal process booting time, and they can also be hard to migrate it for the virtual machines. So the root cause here about the usability of the current enclaves is that to ensure its security guarantees, we must have the spatial isolations and the execution isolations of enclaves to separate it from the other normal applications. In contrast, to introduce more common features into the enclaves, we must introduce new feature extensions by implementations, which are always equipped some kind of privileges. And these privileges will guarantee or grant the services more spatial control and execution control over the normal to be provided the normal enclaves. So that is how the previous works have been done. They provide the TE extensions based on one kind of the privilege separation to draw a boundary between the enclave codes and their target feature extensions. And this work has been done by multiple previous works in the security Symposium, such as to introduce the memory sharing, they extend the privileged mode secure monitors, and they also introduce some control thread inside the enclaves to ensure the serverless computing, confidential computing in the serverless scenarios. So to summarize, where to put the extensions for the feature extensions in the enclave? So the first design is to put our feature extensions inside the enclave, or we can call it intra-enclave compartmentalization, which means that first we introduce one privilege layer inside the enclave code. However, we instrumented the original code to let it call the privilege layers to satisfy to enjoy the services provided. However, this kind of implementation will lack of the architecture level protections, and it also depending on the bug-free software implementations for the feature extensions. And the second solution here is that we could introduce the extensions inside the privilege mode in the whole machine by introducing trusted modules or the trusted trampolines inside privilege mode. However, when we want to introduce multiple, when we try to introduce various feature extensions, or we want just to integrate multiple extensions together, there is a TCP problem. That is, we introduce too many things into the privilege mode, and it will cause heavy TCP burden. For example, when we want when one enclave just wanted to enjoy the inter-enclave memory sharings, it do not want to trust this code in the memory introspection features. So that is called the TCP burden. And it also violates the principle of least privilege. So the third and the last design here is that we could introduce the inter-enclave privileges, which means that we could put the services inside the enclaves and to let the enclaves themselves to manage their some small lower layer privileged normal enclaves. And here we could design a parent or parent-children enclave tree. And it also has some advantages. First, it could have architecture-based security. This is because we could introduce the parent-children enclave or the inter-enclave privilege separation design into the firmware extension in the privilege mode, which means the architecture level based security guarantee. And it also uses only the necessary extensions to minimize the TCP in comparison with the privilege mode extensions. As we can see in here, the unused extensions are excluded from the necessary TCPs for the normal enclaves. And the third one is that we could make the extensions programmable. This is because when we try to introduce one feature extensions, we need to rewrite the secure monitor, or we need to modify the code in the privilege mode, and that is complicated, and we need to be careful because when we have a bug in the privilege mode, it will cause significant security vulnerabilities in the privilege mode. In contrast, if we could program all the feature extensions in the user mode in the service enclave, that could be easy, and the programmers it will be easier for the programmers to introduce new feature extensions. And this has been done and surveyed by some previous works like the nested enclave and the capstone. However, they have some limitations, such as they only guarantee the single layer privilege separations, and they do not introduce the formal security definitions about how to define the security property about the privilege separations. So that is also the two challenges here. The first challenge is to introduce the security definition of the parent enclaves and children enclaves privilege separations, which means that when the children enclave is compromised, it should not introduce any threats for the parent enclaves. And the second challenge here is the scalability. As we can see that how many layers could we introduce for the privilege separations? As we all know that the previous works only introduce first one layer, and that is not enough for the real-world use cases, as we will show soon. So that is how our work knows a formal approach to multi-layered privilege for enclaves. So our threat model is also similar with the original TEE platforms. We assume the malicious OS, and we also exclude the side channel attacks and the denial of service attacks out of scope. And we concern about the security of one privileged enclave when any of the non-ancestor enclaves are compromised. So to solve the challenges about the security and scalability, we have solved them by our formal approaches and engineering efforts. So for the security part, we will give the formally verified security properties and the enclave model based on one previous work on defining the abstract formal model. And for the scalability, we have proved the security for any unlimited layer number for the privilege separation, which means we could introduce unlimited privilege separations for the inter-enclaves to provide feature extensions. So to solve the first challenge, to define the security, we need to define the privilege instructions over the privilege separation layers, which means that how many privilege should we guarantee to the privileged enclaves to help it manage its children enclaves? As you can see that there is a table here for the operations. It could the one privileged enclave could launch one or create one normal enclave and could enter its execution trees, and it also can, in contrast, execute and destroy it. It also can inspect its contents, its memory contents of the normal enclaves. And you can see that we could build one privilege separation layer tree here with one operating system as a privileged software and one several most privileged enclaves. And the most privileged enclaves could also introduce some less privileged enclaves, and they could build a tree here. And we also build an abstract enclave formal model to formalize the whole implementations by extracting all the 7 instructions. And we also define the security remote computation property as the security property, which means that the security property here is including the integrity and confidentiality. For example, for the integrity, it means that when one enclave is created, for any adversary, it cannot modify the contents of all the security data here. And this is formalized by our first-order logic. And finally, we use the security prover and inductions to verify the whole security property. And we can also build a proof tree here. The top SRE property is the Go security property here. And the bottom layer here is the basic features that provided by our multi-layered privilege extensions. And to prove them, we introduce some lemmas here. And to solve the scalability about the multi-layered privilege, we introduce the inter-enclave. Let's see what is this challenge here. So this is because that when we introduce the inter-enclave privileges, and the privileged enclave have the control over the execution flow about its non-privileged enclaves, then it will introduce new execution flow from the privileged enclave to the non-privileged enclaves. So by our formal analysis, the verification state will explode by a double exponential function, which means that if we assume that one normal process could maintain when we assume that one operating system could host at most n process, then for the normal privileged enclave, its model complexity will be polynomial n. And after we introduce this kind of privilege separation, its verification state will explode to a double exponential function about the n. To solve this, although we cannot just easily cross the gap about the theoretical bound, but we can use the necessary optimizations and the induction proofs to prove it by some of tricks. First, we redefine the security properties using the scholomization, which means that we unify all the security layer properties by a universal quantifier. And we also use the relevancy post-propagation property in the Z3 solver to help the Z3 solve all the properties by only tracing the relevant parameters that modified in the whole deductive proof procedures. And some of the proofs are hard to get across. Then we use some inductions here to parameterize all the privilege separations, which we will discuss later. Okay, sorry. And for the implementation part, I will shortly discuss that. For the evaluation here, we can see that our verification time is just will cost about 12 hours, and which is the greatest gap between than the previous 5 minutes, which also verifies that our gaps in the model complexity. And for the implementation part, we can guarantee that we only introduce about less than 5% overhead in the context switch and all the CPU intensive overheads. And we also evaluate our implementation using hierarchical deterministic wallicks and erasable enclaves to introduce multiple feature extensions together into our privileged enclaves. And this is our artifact here, and that's all. Thank you. And we are open to any questions.
Thank you, Genshan. I think we have time for one very short question.
Okay.
What TE do you use?
The Penglai TEE platform here.
RISC-V?
RISC-V, yeah.
Okay, let's thank the speaker again.
Thank you.